So today I'm going to talk about order of an element modulo another number. I'll recall the definitions in a bit. And here in this section, in this couple of lectures, the goal is to do a quantum algorithm for factoring numbers into prime numbers. The main tool that's going to be used algorithmically is going to be the quantum Fourier transform. And when I was figuring out how to present this material, I was debating whether I should skip some of the math and just get straight to the algorithm. But I decided that we should spend more time in the math. I think the algorithm works, and we can check by computations and experiments that it's accurate. But what I'm more interested in is why the algorithm works and the structure and the math behind it, and in particular, why the quantum Fourier transform is applicable here. And I think this helps us see how to apply the quantum Fourier transform in other applications. And in particular, that's where the speed up in this quantum algorithms is going to lie, in the quantum Fourier transform. And that's why I'm particularly interested in understanding how the quantum Fourier transform appears in this setting, or what's the mathematical structure behind it leading to the quantum Fourier transform. And in particular, it turns out that if you have a problem that is you use Fourier transform, then you can apply the quantum Fourier transform and then have the quantum speedup. So for this, I wanted to see how the Fourier transform appears in the problem of factoring numbers into prime numbers. And so for that, we're going to delve more into the theory, the math theory, and in particular number theory, and see how this is appearing in the structure. And it's a bit subtle, so it's going to take a little bit of effort. It's going to take a lot of some computations, and some lemmas, some statements. We're going to be building some of the things from the ground up. But at the end of the day, the arguments are not too sophisticated, and we should be able to follow them. Here, I remind you the factoring strategy, the overview that we're going to take for doing the Shor's algorithm for prime factorization. First, we assume that the number n that we're trying to factor is not of the form p to the alpha. And if it is of the form p to the alpha, then there's classical algorithms that can figure this factorization pretty fast. It doesn't require the quantum algorithm. We also assume that p is greater than 2. Oh, p is greater than 2. And if p is equal to 2, then again, there's classical algorithms that are pretty fast. So at the end, we're going to assume that n is not a prime power. But in some of the computations that we have, we'll prove statements for any n. But in any case, so having this assumption, the strategy for factoring n is that we choose an x randomly between 1 and n, and then we find a positive integer r such that x to the r is equal to 1 mod n. And if r is even, then we get that the GCD of one of these two GCDs with the plus or the minus is going to be a factor of n. So either the GCD of x to the r over 2 plus 1 and n is going to be a factor, a non-trivial factor, or x to the r over 2 minus 1 is going to be a non-trivial factor. So of n. You say non-trivial. So there are two things to remark here. First, there's two important steps here. One is finding R, and this is called the order of x modulo n, and that's where the quantum speedup appears. This is where we're going to do the quantum Fourier transform to find R, and this is where we're going to have our advantage. This is where we apply our quantum algorithm. And once we have it, once we have R, the order, we have to get lucky in some sense, because we want R to be even. And this depends on the choice of x. And if we choose, depending on how we are on the luck of choosing x, then it may not be even. And so what we'll actually prove is that with high probability, R will be even. So part of the statements that we will prove is that this condition is highly likely, depending on x. So these are the main ingredients of the factoring strategy. And here, this is going to be the quantum speedup. And we're going to spend now time doing the number theory and thinking about this type of problems, finding R such that x to the R is equal to 1, and finding the different properties of what R has to be and in what cases R is going to be even. So this is going to be the number theory aspect, the math, the structure. Any questions so far? Does the factoring strategy make sense? All right, so we're going into a lot of number theory. So let's recall some definitions. And the first is the order of x modulo n. I'm introducing this notation that for the order of x modulo n. Oops, this should be an n. So for the order of x modulo n, I'm just going to define this notation, and then this is going to be equal to R if R is the minimum element, positive integer, such that x to the R is equal to 1 mod n. And in the previous class, we discussed that this is a non-empty set, and this is a non-empty set, and we can find such an R as a result. And here we should have a condition that the GCD of x and n is equal to 1, the greatest common divisor, for this definition to make sense. The other definition is the Euler phi function. I'm introducing this set. This set here is going to be the elements modulo n such that the GCD is equal to 1. So it's going to be all the numbers between 1 and n such that the GCD of x and n is equal to 1. And the remark here is that if you have this condition of the GCD equal to 1, then you have a multiplicative inverse of x in mod n. So in here we have, if we have this condition, then we have that we can write 1 as a linear combination of x and n. And then if we take the mod n of this equation, then we have that alpha times x is equal to 1. And we have that x inverse is equal to alpha. And in particular, this means that all the elements in this set have multiplicative inverses. So we can multiply things and we can divide things. So this is going to be the subset of elements of C mod n that have multiplicative inverses that you can multiply and take division. So it's a subset. If you have GCD greater than 1, then it's not gonna be in that set, but those elements don't have inverses. And the Euler phi function is defined to be the size of this set, the cardinality of this set. So far, so good. Any questions? Yeah.
So this would be the set of all x that are relatively prime to n that you can divide with.
Yeah. Yeah. So, and this is, in particular, one of the motivation is because in here, what we're trying to find is the order of x. And for the order of x to be defined, we need to have that the GCD of x and n is equal to 1. So we're just considering these elements. And so we're considering the structure of these elements. All right. So let's do a quick exercise to make sure we understand the definitions. Let's take a few minutes and try to compute phi of p alpha, where p is a prime and alpha is a positive integer. The hint is to consider phi of 3 and phi of 3 squared and see if you can find a pattern. And here's the definition. And the question was phi p alpha is equal to what?
Can you go back to that?
This one?
Yeah.
What's phi of 3? 2. What's phi of 3 squared? 6. All right. Does everyone agree? Now turn to your neighbor and see what you have for phi to the alpha. See where you stand. Any answers to the question? How far did you guys get?
It seems fairly clear that phi of p is p minus 1.
Okay, so we got alpha equals to 1. Phi of p is equal to p minus 1. And any alpha 2? Any guesses?
And tested for 5 as well. It seems like, well, in one case I can multiply by, so for alpha equals 2, it might be p minus 1 times p.
Is that what everyone else got? How about for alpha greater than 2?
Yeah,
Yeah, is that your guess?
that's what I was trying to like put together the algebra for, but that's what I was, yeah, that would work.
So let me just sketch the idea behind this. In here, you're looking at, I'm counting this by exclusion. I'm counting the numbers that have GCD greater than 1. This is p to the alpha. So I'm just going to subtract it from the whole set. And here the elements that have GCD greater than 1 have to have a common factor with p to the alpha. And since p is prime, they have to be multiples of p. So in here, the elements that have GCD greater than 1 is going to be p squared, and all the way to p to the alpha. These are the elements that have GCD greater than 1. Does that make sense? So then the count is that the total number of elements in C mod p to the alpha C is going to be p to the alpha. And how many elements are here? Alpha? Oh, sorry. There's a typo. Mistake. It's all multiples of p. 2p, 3p, all the way to p alpha minus 1p. So how many elements? Yeah, p to the alpha minus 1. So this then gives us that by the exclusion rule, it's got to be p minus p to the alpha minus 1, which you divide the p minus 1, and you get p alpha minus 1. So this is the formula. And in general, for the other, if the number here is something else, it's a product of 2 primes or more primes, then you can do a similar approach of counting the multiples. And we'll get to it eventually, but in here, this is the formula that we're interested in, and we'll be using it in the next statements. That the phi of p to the alpha is going to be equal to p minus 1 times p to the alpha minus 1. Questions? All right. So this is Fermat's, generalized Fermat's little theorem that that x to the phi to the n is equal to 1 mod n if the GCD of x and n is equal to 1. And in here, this is what we're going to be using for figuring out the order of r, the order of x mod n. And in this case, I'm going to give you a partial proof for the case n equals p to the alpha. Later on, I'm going to all these arguments, I'm going to generalize them to actually have multiple primes. But for that, I need a specific tool, the Chinese remainder theorem. But in here, these are all the base cases for a single prime. And then using the Chinese remainder theorem, we'll eventually put everything together and generalize everything. But in the meantime, I'm just going to be working this special case. And then by this base cases, I can put everything together and cover all the cases. So this is going to be an induction on alpha. And the base case is Fermat's little theorem. So for alpha equals to 1, we have that x to the phi of p equals 1 mod p is equivalent to x to the p minus 1 equals 1 mod p. And this is the result of Fermat's little theorem, which we proved last class. Now, for the alpha greater than 1, we do induction. We assume the statement is true for alpha equals k. And we show that it's true for alpha equals k plus 1. So from the alpha equals k case, we have this statement. This is the assumption, the induction hypothesis. And we know the formula for this phi function. We just derived it. It's going to be this number. So this is an equivalent statement. It's the same statement. And from this statement, we know that x to the p minus 1 times p to the k is going to be equal to 1 plus m times p to the k, because this is an equivalent statement. And then we just compute the p power of this and modulo p to the k plus 1. So we do the p power of this, so it's equivalent to putting a p power here. And then we do the binomial theorem. We just expand this. And so these are just the binomial coefficients, and we do the expansion. And in the previous class, we showed that all these binomial coefficients, if the number on top is p, are going to be divisible by p. So all the coefficients in here are going to be divisible by p. So this is divisible by p, and this has a power p to the k. So the total power of this and this is going to give you p to the k plus 1. And mod n, this is going to be equal to 1. So equal to 0. So this is going to be 0. And similarly here, this is going to be it's going to be equal to 0 mod p to the k plus 1, and so on. And so in here, this is equal to 1. This is an exceptional case. But in here, p to the p is going to be divisible by p to the k plus 1, just because p is large. And actually, this is p to the kp. P to the kp. And so we get that the statement is true for alpha equals k plus 1. And this wraps up the induction. In here, this is the main tool and the main strategy for most of the proofs that we'll have. It's going to be the binomial theorem. We're just going to do binomial expansions. And the idea is that these coefficients are going to be divisible by p, and then we can handle the modular arithmetic that way. So this is the basic idea happening in all these statements. Any questions? All right. So this is going to be the main claim that we need for our factoring strategy. We need to find that the order of x mod n is divisible by 2. And this is going to be one of the goals for the next lecture. We want to prove that the probability that the order is even, and there's this additional condition that this is not equal to minus 1, x to the r over 2 is not equal to -1, that this probability is going to be high. And so if n is of this form, then the probability is going to be the lower bound for the probability of actually picking a x at random that has the properties that we want to factor n is going to be given by this lower bound. And the thing that you should note is that the more prime factors that it has, the higher the probability that you'll find a factor. So in here, it becomes increasingly likely that you'll find an appropriate x where you can find a non-trivial factor of n. So this is going to be the goal, the precise statement of what we want to prove for finding an appropriate x, to actually establish that the algorithm works with high probability. And in here, I'm going to work on the base case. Again, this base case, we'll be able to generalize this base case to the general case once we introduce the Chinese remainder theorem. But right now, we're just working with the base case and establishing all the techniques there. And then the generalization just takes the base case and the Chinese remainder theorem to prove everything. Yeah.
What was the last values to the what?
M minus 1. So M is the number of prime factors. So if you have more prime factors, it's more likely that you'll find something right, that you'll find the appropriate x. All right. Any other questions? So in here, I'm going to take n to be just a prime power. P is a prime, alpha is a positive integer, and I'm going to take an x in this set, meaning that the GCD with respect to p to the alpha is equal to 1, meaning that it's not a multiple of p, and I'm going to pick it uniformly at random from all of these possible elements. Then the claim is that the order of that x, mod p to the alpha, is going to be 2 to the d, with probability equal to 1/2, where 2 to the d is the largest power of 2 that divides p minus 1. P is going to be an odd prime, so p minus 1 is going to be even, so d is automatically greater than or equal to 1. So this is the condition. This says that the probability that x is even, and in particular 2 to the d, is actually this statement is, I need to fix this. I actually need to say that 2 to the d, the probability that 2 to the d divides the order is equal to 1/2. So the probability that the order is even is going to be 1/2 in this case. And so this is the base case that we're going to prove, and then we're going to generalize it to the main claim that we want for the algorithm to work with high probability. In this proof, I'm going to use a fact that I'll come back to afterwards, is that for this set of numbers, there exists an element g such that we can write this set of numbers as powers of g. In particular, g is going to generate this set. So all the elements in here are going to be powers of g. So we can write every element in this set that way. And this is particularly useful because we're choosing elements from this set uniformly random. And this representation of the set is going to be convenient to proving this statement. And we'll prove this representation. So before we go to a proof, we're gonna do a warm-up to make sure that we're on the same page. So assume we have an x such that x to the n and x to the m is equal to 1 mod n, and n is minimal. Both n and m are positive integers. N and m are positive integers. Show that n divides m. So take a moment to work on that. Is equal to questions? All right, turn to your neighbor and see where you stand.
Yeah, suppose like suppose n and then you can say then x to the m is not equal x to the k n. Here's like minus mod n, which is equal to 1 because x to the n is not. I feel like that saving or something. It's just like young limit or not. So. Okay, and this is true, like here, yeah. I'm not sure it's greater than it's so then this is going to be a factor of that.
All right, so does anyone have any leads of where to start? Any leads over there? You guys have any leads?
Yeah, so we can write x to the n as x to the n s plus r. And then the breakout part and the ns part is just 1. Now xr is equal to 1,
Okay.
but n was supposed to be minimal and r smaller.
Yeah. Does that make sense? And here we have that R is, we have this condition that R is between 0 and n minus 1. And since n is a positive integer that has to be minimal, then that means that R, to not have a contradiction, R has to be equal to 0. Otherwise, it would break the contradiction that, it would break the contradiction that n is minimal. Questions? Yeah?
I made a different proof, it's slightly different. So like if you just say that, if you suppose that n doesn't divide m, then x to the m does not equal x to the Sn. And then, but x to the Sn does equal 1 mod n. So then you have, I feel like there might be something weird with the modular arithmetic there.
Yeah.
That prevents you from saying that. But.
Yeah, that may work potentially, but I think this is a more straightforward way to do it. Do you see it this way?
Mm-hmm.
Yeah. Everyone else sees it this way? I see some confusion here in the front row.
I'm a little confused.
All right.
Why does m equal Sn plus r? I don't know. Shouldn't m just equal Sn?
So for any numbers m and n, you can just, this is just division. This is division with a remainder. So if I have like, say...
But wouldn't r have to equal 0 for...
we don't know if it's divisible or not.
Okay.
So for any numbers, say 5 and 3, you can write 5 is equal to 1 times 3 plus 2. This is going to be s, and this is going to be the remainder. This is the number of times that 3 goes into 5, and this is going to be the remainder. So for any two numbers, it's a general thing for any two numbers, you can divide with a remainder. So this is going to be the number of times that n goes into m, and this is going to be the remainder. And the remainder has to be between 0 and n minus 1. So we just know that for any n and m, we can write it this way. And what we're trying to show is that r has to be equal to 0 so that it's a multiple. And we see that if r is not equal to 0, we start from this left-hand side. We have this assumption that 1 is equal to x to the m, and then we use this representation, which is true for any n and m. And then we know that x to the n is equal to 1, so this is going to be 1. And then we have that x to the r is equal to 1. And r could be a number between 0 and n minus 1. Bless you. And since n is minimal, then it has to be 0.
Okay.
All right. Great.
Is there an argument you can make with like factors though? Like because it's modulo n, then like
I'm not sure what you mean.
like both xn and xm being have to be factors
Of the order. So we.
of the order, yeah.
Well, this is kind of getting to it that they have to be factors of the order. So any n and m are going to be, so this is going to be a corollary of this statement is that any n and m that we have is going to be, we know that the minimal n is actually equal to phi to the n. This is what we said. So this is saying that if you have any m where x to the m is equal to 1, then this is going to mean that phi to the n divides m.
Yeah, okay.
So this is what we're getting at, that we're showing how phi is going to divide different powers if we have this condition. Because in here, what we're trying to do is to show that we're going to look at different x's, and we're going to look at their power, r, at their order, r, and then we're going to see if it divides, if 2 to the d divides it or not. So this is going to be, this is going to be the strategy. If we have it, the order is r, we're going to show that phi to the n divides it. So here's a proof. So again, this is for this special case, phi of p to the alpha. In this case, we know the formula for this function is going to be p minus 1.
I had one question. Go back. Yeah. Oh, you fixed it.
Yeah, I fixed it. Yeah,
Okay.
thank you.
All right.
So in this proof, now we first note that we know this formula, and then we define, bless you, 2 to the d to be the highest power of 2 that divides p minus 1. And since p is a prime, it's an odd prime, it's not going to have any more powers of 2, so we can write this phi as 2 to the d times m, where m is odd. And now, by the previous fact that we have that we can write any x as g to the k for some k. Any x can be written of this form, g to the k. And we'll set r to be the order of this x. So then the proof breaks into two cases. This k is even, or this k is odd. And in the case that, and it turns out in the case that it's odd, then the order is going to be divisible by 2 to the d. In the other case, it's not going to be divisible by 2 to the d. And since half of them are odd and half of them are even, that's going to be the probability 1/2. So in one case, it's going to be in the odd case, it's going to work out. And in the even case, it's not going to work out. So half the elements, it's going to work out. So that's going to be probability 1/2. So in here, we have x to the r, by the definition of the order, we have x to the r is equal to 1. And that means that g to the kr is equal to 1. And by the previous exercise that we have, that means that the order phi of g divides kr. And so that means, and since this is odd, and k is also odd, then that means that the even part must divide r. Does that make sense? So in this case, in the odd case, it does work out. And in here, I remove this elements from this 2 to the, from this divide relation, because m is odd and k is odd. So 2 to the d cannot divide an odd element, and that means that it has to divide this part, the r. Now, we'll show that the k-even case doesn't work out. It's a similar idea. Now we have that 1 is equal to g1 is equal to this, to g to the k over 2 to the phi of p to the alpha. This is from the generalized Fermat's little theorem. Any element in the set that we're considering you can take the power to the phi to the alpha, and it's going to be equal to 1. So this is true for any element in Z mod P alpha Z star. So in particular, it's going to be true for this element. So this is true from the generalized Fermat's little theorem. And then I move around the exponents. And I have g to the k, which this is going to be x, to this power is going to be equal to 1. And since r is minimal, that means that r has to divide this power, this exponent. And in here, we know the formula for phi of p to the alpha. It's 2 to the dm, and I divide by 2. So I get that r divides this number. And since r divides this number, then it cannot divide a higher power of 2. That's the highest power of 2 to the d that it divides. So it's not going to divide this element of r. This r is not going to divide this 2 to the d. And we're going to have that only the odd elements are going to be divisible by 2 to the d. And that's half the elements, so that's probability 1/2 of our statement. The probability that 2 to the d divides the order of x is equal to 1/2. So it's only going to be for the elements that have a odd exponent. Questions? Oops. All right. We have 2 minutes left. We'll pick up with this in the next lecture. I want to prove this fact that we can write this set as powers of g for some g, and the statement relies on this. That proof relies on this statement, which I picked up from the book from Donald Knuth, The Art of Computer Programming, Volume 2, page 17. Spoiler alert, it's just the binomial theorem again. So that's what we're going to do. That's class. Have a good weekend.